Hello, this video is about absolute extrema. Let's first begin with the definition. Let's let f be a function that has domain D. Then f has an absolute maximum value on that domain at a point C if f of c is greater than or equal to f of x for all x in that domain. So think about what that's saying. The f of c is bigger than the rest of the function. F will have an absolute minimum value on D at a point C if f of c is less than or equal to f of x for all x in the domain, which means that point when you plug in c, f of c is smaller than the rest of the function. Together, these are called absolute extrema. So if you say absolute extrema, you're talking about the absolute maximum and the absolute minimum in general. Sometimes these are also called global extrema. I will generally call them absolute extrema. All right, so let's look at this in some pictures. Okay. This first function on the left, we see that it does have an absolute minimum. This point right here, 0, 0, is on the bottom, is below every other point of the graph. This graph does not have an absolute maximum value. And that's because we can think about how these two tails of the parabola keep going up forever. There is no absolute top of this graph. There is no absolute maximum that it attains. All right, this minimum, we see that it does have an absolute max right there at 2, 4. And it seems to have an absolute min at 0, 0. So we see an absolute min there. When we're looking at the absolute max and absolute min, we're paying attention mostly to the y values. How high does this graph go and how low does it go? Okay, on this third one, we see that it does have an absolute max, kind of same as the other one at 2, 4. However, there is no absolute minimum value. Notice our point is open. We don't quite get to 0, 0. So there is no absolute lowest value here. You can think it's just approaching that point 0, 0, but it never quite gets there. So no matter what point you would say, oh, well, it's like 0.1, 0.1 or something, there's always something smaller than that, 0.01, 0.01. We can always get a smaller x value to plug in, which will get us that smaller y value too. So there's no absolute min. All right, let's look at these. This one's sort of the reverse. This one has an absolute min, right there, 0, 0. But it does not have an absolute max. There is no absolutely the largest that this graph gets. Notice it's getting really, really close to 4, approaching 4, but it's not quite getting there. So it's 3.9. Maybe you say, okay, well, the absolute max is 3.9. Well, then I could counter and say, well, it gets up to 3.99, and then someone else could say 3.9999999, but there's no end to that. We can always get a little bit higher than any point we say, so there is no absolute maximum. And then this last one has no absolute max or min. For those same reasons we were just looking at, those circles are open, those points are open, so we don't quite attain that maximum value of 4 where we're heading towards. We don't actually get there, nor do we attain that minimum value of 0. We're just getting really close to it. All right, so we have something called the extreme value theorem. If our function f is continuous on a closed interval a to b, then we are guaranteed for that function to have both an absolute maximum and an absolute minimum on that interval. So where can these absolute extrema occur? So notice in both of these graphs, I have continuous functions in both pieces, and they're on a closed interval, which means they're colored in at the end from 0 all the way to 2 pi. We can think of this interval as 0 to 2 pi. And this interval is 0 to 3. So they are closed intervals. Now, where can these absolute extrema occur? Well, if I'm looking at this left one, I see an absolute max right here. And I see an absolute min down here at 3 pi over 2 negative 1. And notice both of these are on the interior of the interval. So the extrema occur, write that too, on the interior. All right, for this next one, this other little piece that we have, I see the absolute max is here at 0, 2, and the absolute min is here at 3, 1. And notice here the extrema occur on the endpoints. So that can happen as well. There we go. We can also kind of mix and match. If we look at this one on the left, I have an absolute max. It looks like, I don't know, 1.2 comma 1.2 or so. We're just kind of estimating. So we've got an absolute max there. And here's our absolute min. Remember, again, we're looking at what is the highest this graph ever goes and what is the lowest that this graph ever goes, according to the y values. So here they're mixed. The absolute max is in the interior. And the min is an endpoint. And then we sort of have the reverse over here. Our absolute max, I guess it's about 3 comma 1.5. The max is at an endpoint. And the minimum value here, which at 1, 0, the min is on the interior. So we can mix and match. Your absolute extrema can occur on an endpoint and can occur in the interior. And if the max is 1, the min doesn't have to be something specific. We can mix and match all those situations. All right, so here's an important note. The function must be continuous on a closed interval for this theorem to apply. If one or both are not met, then we may or may not have absolute extrema. We can't guarantee anything. So an example, what if we had a function that looked like this? And those arrows kind of implying that it's going down forever on each side. Looking at this one, I haven't restricted it to any closed intervals, so I'm not guaranteed that I'm going to have them. Now I do. Notice this one does have an absolute max, but there is no absolute min. And we weren't guaranteed one because we were not on a closed interval. So this is not a closed interval. Okay. So if you want to guarantee that you have both an absolute max and an absolute min, you must be a continuous function on a closed interval. All right. So another thing that we want to look at is the idea of relative extrema. So let's look at the definition. A function is going to have a relative maximum. Sometimes these are also called local, relative or local. I may say both. I'll generally say relative, but local means the same thing. But a function is going to have a relative maximum value at an interior point of its domain if f of c is greater than f of x for some open interval including c. So let's contrast this to the absolute extrema. The absolute extrema, your point had to be higher than every point in the entire graph that you were looking at. Now, a relative extrema, it doesn't say every point, it just says some open interval around it. So a relative max is just bigger than everything right around it, is the idea. And similarly, a relative min, or a local min, is just smaller than everything right around it, okay? You can think about Mount Everest is the absolute max for the world. It's the highest point in the world. But all the other mountain chains, all the other mountains are relative maximums. They're still higher than everything kind of right around it, but they are not absolutely the highest point ever. Relative minimum, a small canyon would give you a relative minimum, but wherever the deepest canyon is would be the absolute minimum. So let's look at an example. Let's label all of our absolute and relative extrema on this graph. Now, before we get started, that extreme value theorem is going to apply because notice this function is continuous and it is closed. Notice our endpoints are included. So we are guaranteed to have an absolute max and an absolute min. Let's start with those. Let's start with the absolute extrema. This point up here is going to be my absolute max. That is as high as this graph ever goes. And then this point down here, like, I don't know, like 2.7, negative 1.9 or so, this is my absolute minimum. That is the lowest this graph ever goes, the smallest y value it ever attains. So now let's go to relative extrema. Now remember, relative extrema don't have to be the biggest in the entire graph. They just need to be bigger than everything right around it. So this point looks about negative a half, comma, I don't know, 1.9. This is a relative max. Notice it's sort of the top of a mountain. It's bigger than everything right around it. And I see another relative max right here at about 1.5, comma, 1.7 or so. Again, it is bigger than everything right around it. All right. Over here at about 0.5, negative 0.7 or so, I see a relative min. It's not the smallest, the lowest this graph ever goes, but it is the lowest of everything right around it. And then I notice that my absolute minimum is also a relative minimum, and that can happen. Okay. One thing I do want to point out, we may be tempted to say that this endpoint is a relative max, or this endpoint is a relative min, but let's flip back to our definitions. Notice that our relative maximum and relative min are defined, they're saying an interior point. We're talking about interior points. So we're not going to include our end points as relative extrema. All right, so we have labeled all of our relative extrema and of our absolute extrema. All right, so how do we find extrema? Well, relative extrema are going to occur at what we call critical numbers or critical points. Our specific book says critical numbers. The book I learned out of originally says critical points, so I'm probably going to say critical points just because that's what's natural to me. But critical points, critical numbers, the same kind of idea. All right. So what are these critical numbers? Well, these are numbers where either the derivative equals 0 or the derivative is undefined. Let's flip back a few slides. Come back over. Where were we? Oop, I thought maybe it's, here it is. So notice, just kind of glancing at this one, this would be a point over here on the right with an undefined derivative. And notice it's kind of, if we try to draw our tangent line, it's going to be vertical. And notice that's going to be undefined, and that's where a minimum did occur. Notice this one would also be a relative min, but we just weren't talking about it yet. And then notice here, this absolute max or this absolute min, we're seeing a horizontal tangent. So that means the derivative is 0 where these extrema are occurring. Let's flip back. We can look at it here too. We'll draw some lines on here. We're seeing a horizontal tangent, a horizontal tangent. All these horizontal tangents are happening where these relative extrema. So it's either a horizontal tangent, that's the derivative is 0, or the derivative is undefined, and that's going to be a vertical tangent. Okay. So this relative extrema occurrence, so if f has a relative minimum or a relative maximum at some point c, then that c was a critical number. So notice, though, that the converse is not necessarily true. If you find something that is a critical point, then that doesn't mean it will be an extrema. So a quick example here, let's look at the function y equals x cubed. So our derivative, y prime, would be 3x squared. And so if we take that 3x squared and set it equal to 0 to find our critical points, notice that x equals 0 is a critical point. And I'll often just write CP for critical points. Okay, so x equals 0 is a critical point means it is a candidate for a relative max or a relative min. It doesn't mean that it automatically is one. And let's think real quick, if we were to graph x cubed, what does x cubed look like? Well, we know it looks something like that. And notice right here at 0, where we were talking about, this is not a relative extrema. Okay? So when you find your critical points, you are finding candidates for your relative extrema. You're not finding what are specifically will be the relative extrema. You're just finding candidates for it. All right, so how do we find our absolute extrema? So step one, we need a continuous function on a closed interval for that extreme value theorem to apply. Step 2, we're going to make a list of all of our critical points that are in our function in the interior. We're not going to include any critical numbers that are outside of the interval because we have zoomed in on some closed interval. Therefore, we're not going to include any critical points outside that interval. We're going to add our endpoints to that list. Remember, your absolute extrema can happen at an endpoint, so let's add those to our list. And then we're going to evaluate the function at all points on our list. Whatever our smallest value is, our smallest f of x or our smallest y value, that's our absolute minimum. And the biggest is going to be our absolute maximum. So let's go through some examples. All right, so let's find the absolute extrema of this function 3x to the fourth minus 4x cubed on the interval -1 to 2. All right, so our first step is we need to find our critical points, and we find critical points by saying where is the derivative equal to 0 and where is the derivative undefined. So f prime of x is how we'll do that. So if we take our derivative, we get 12x cubed minus 12x squared. Okay, so there's our derivative, and we want to see where is this derivative equal to 0 and where is it undefined. First of all, this one's never undefined because it's a polynomial, so we don't have to worry about any critical points coming from the derivative being undefined. Let's set equal to 0 now. So we have 0 equals 12x cubed minus 12x squared. And here's where we want to factor. When we're setting something equal to 0, we want to factor it as much as possible to see what the values for x are that solve the equation. So I can factor out a 12x squared, and I'm left with x minus 1. So I can set each piece equal to 0 now, and that implies that x equals 0 and x equals 1. So I get x equals 0 from here and x equals 1 from here. So what I can think about is I'm making a list of all my x values that are critical points and that could possibly be absolute extrema. So 0 and 1. Quick spot check. The interval I'm looking at is -1 to 2. 0 and 1 both occur on that interval, so I'm going to include them. Okay. All right. So I found where my derivative equaled 0. It's never undefined, so I don't have to worry about it. And now I also want to throw in my endpoints, -1 and 2, and test all of them. So just kind of, we'll make a little note. This is an endpoint. This is from the derivative equals 0. This is from the derivative equaling 0. Oops. Derivative equals 0. And this is from an endpoint. So these two are critical points because they cause the derivative equal to 0. Now again, remember, critical point doesn't imply it's going to be an extrema. It's just a candidate. Okay. All right. So now we're going to find f of x. Now be careful here. We are plugging back into the original because we want to know where is this on the original graph. So if we plug -1 back into f of x, go back to the very original here, plugging in a -1, we're going to get a 7. If we plug in a 0, we get a 0. If we plug in a 1, we get a -1. And if we plug in a 2, we get a 16. I know I did that quickly, but I'm trusting that you all can plug those in quickly either by hand or on a calculator to get those answers. Now, what we want to do is determine what is our absolute max and what is our absolute min. So I'm going to look at my f of x column for the biggest number and the smallest number. Here I see my smallest, so this is where my absolute min. And here I see my biggest, so this is my absolute max. So I would say absolute min at 1, -1, and absolute max is at 216. And just some notational and kind of the terms you would use kind of surrounding this question. If someone asks you what is the absolute maximum value of this function, the absolute maximum value is 16. The highest this function ever goes is 16. Now, if someone said, where does that absolute max occur? You would say at the point 216 or when x equals 2. Okay, so the absolute maximum value is 16. Where does it occur? At the point 216. The absolute minimum value is -1, where does it occur at the point -1, -1? Okay. All right, let's do another one. So again, we want to find the absolute extrema. We'll start by taking a derivative. So here our derivative would be 2/3 x to the -1/3. And we want to figure out where is this function undefined and where does it equal 0. Here is a situation where now we want to possibly rewrite it in a better form so that we can more easily determine where it equals 0 and where it's undefined. So I'm going to rewrite this as 2 over 3 times the cube root of x. Or I can think 2 over 3x to the 1/3. Both of those are okay. But what that does for me is now I can analyze where does it equal 0 and where is it undefined. So where is f prime equal to 0? Well, that means set it equal to 0. So 2 over 3 times the cube root of x equals 0. And notice if I multiply both sides by that denominator, I'm going to end up with 2 equals 0. Ooh, that's weird. So the answer is never. This derivative is never equal to 0. And we could have actually seen that from the beginning up here when we were looking at our derivative. We have a constant on top of our fraction. So if you have a fraction where the top is a number, well then that fraction is never going to be able to equal 0 because you always have some part of that whole. So this is never equal to 0. Where is f of x? Where is f prime of x undefined? Okay. Well, this function, so 2 over 3x to the 1/3, it's going to be undefined if my denominator is equal to 0. So if denominator equals 0, so we'll say when 3x to the 1/3 equals 0. Well, that is when x equals 0. So it looks like my only critical point I'm going to get from all of this is 0. And I switch back to my interval, and I look 0's on my interval, so it is one that I will want to include and think about. So I'm going to make my list. 0 is my only critical point. So this is a critical point. And then I have my endpoints that could also be. So this will be an endpoint and my other endpoint. All right, it's time to plug them in. And remember to go back to your original and plug them in, because when you're dealing with absolute extrema, you want to know where on the graph it sits. So if I plug in -1, I'm going to end up with, let's see, back to my original 1 to the 2/3. Well, that's just going to be a 1. If I plug in a 0, I'm going to get a 0. And if I plug in a 3, I have 3 to the 2/3. And I'm just going to sort of approximate that to think about what it is. And if I put that in my calculator, it's 2.08. Okay. So that approximation is going to help me compare. So I see my absolute minimum value is 0, and it happens at the point 0, 0. And my absolute maximum value is 3 to the 2/3, and that happens when x equals 3. So absolute min is at 0, 0. And my absolute max is at 3, 3 to the 2/3. All right, let's do another one. So now we have some trig involved. So we want to find the absolute extrema of this function 2 sine x minus cosine of 2x. Okay, so we need our derivative. And the derivative of 2 sine x would be 2 cosine x. And then the derivative of negative cosine 2x, this one's going to need a chain rule, right? Because it's the cosine of a function. So the outside is that cosine, so the derivative of cosine would be negative sine. So negative, but then it was already subtracting. So it would go back to positive sine, leave the inside alone, and then multiply times the inside's derivative, which is a 2. So let's clean this up one step. 2 cosine x plus 2 sine 2x. And one thing I want to note right here, this guy is never undefined. Okay, I can always, the sine and cosine functions are always defined, so when I'm adding them together and multiplying them by 2, I don't really have to worry about that. So what I'm going to worry about is where is f prime of x equal to 0, and that will get me some possible critical points. Okay, so let's set this equal to 0. So 0 equals 2 cosine x plus 2 sine 2x. And as it is, this is a little bit frustrating to solve. So I'm going to use a little trick from trig, one of my identities, and that's that the sine of 2x is 2 sine x cosine x. And why is that change helpful? So 2 cosine x plus 2. Well, now I can trade sine of 2x for 2 sine x cosine x. And I notice I'm going to be able to factor out a 2 cosine x from both pieces. And it's going to be easier to start it to set that equal to 0. So 2 cosine x, 1 plus 2 sine x equals 0. Excuse me. And so now I can set each one of my factor terms equal to 0 and solve. So 2 cosine x equals 0 means that cosine x is 0. And when is my cosine function 0? Well, that's at pi over 2, at 3 pi over 2, at 5 pi over 2, etc. Okay? And now I have 1 plus 2 sine x is 0, which means 2 sine x is negative 1, which means the sine of x is negative a half. So when is your sine function negative a half? So that's going to be down in quadrants 3 and 4. So we're at 7 pi over 6 and 11 pi over 6, and then we could float back around. But I know from the beginning it told me to only look from 0 to 2 pi. So I know I'm okay with just 7 pi over 6 and 11 pi over 6. All right, so let's make our list of our critical points. From down here, these x equals pi over 2, 3 pi over 2, 5 pi over 2, keep going. I don't have to worry about any of these except for pi over 2 and 3 pi over 2. The rest of them are going to be larger than 2 pi and outside of my interval. So I'm just going to worry about pi over 2 and 3 pi over 2. And then I have 7 pi over 6 and 11 pi over 6. You don't have to put these in a certain order, but I just kind of like to have them in the numerical order. Oop, not 2, 6. And then I need to do my endpoints 2, 0, and 2 pi. Okay, so this was an endpoint and an endpoint, and these were all critical points that I found. All right, so now I'm going to plug these in. And remember, you plug them into your very original. You plug them into f of x and see what we end up with. All right, so going back to the original, if I plug it in, if I plug in a 0, I'm going to get a 1 back. I'm going to trust that you can do all this plugging in, so I'm just going to kind of go with what we end up with. If we plug in pi over 2, we end up with a 3. If we plug in 7 pi over 6, we're going to end up with a negative 3 halves. If we plug in 3 pi over 2, we're going to get a negative 1. If we plug in 11 pi over 6, we get negative 3 halves. And if we plug in 2 pi, we get a negative 1. Okay, so that's all of our values there. So now let's see what is our absolute max and our absolute min. Well, we see actually our absolute min is going to occur in 2 places because we have that negative 3 halves showing up twice. So there is our absolute minimum value. And then we do our absolute max is going to be there at 3. Okay. So now we'll just sum this up. Absolute max is at pi over 2, comma 3. Our absolute min is at 7 pi over 6, comma negative 3 halves, and 11 pi over 6 comma negative 3 halves. All right, let's look at one last example. Let's find the absolute extrema of f of x equals x times the square root of 4 minus x on the interval negative 2 to 4. All right, so our first step is we need to find our derivative. And I notice here I am going to need a product rule because I have two things multiplied times each other. So I'm also going to go ahead and rewrite this as x times 4 minus x to the half. That's going to help me find that derivative of that second piece. And I notice I'm going to need a chain rule on that as well. So let's find our product here, our derivative using the product rule. So we'll just leave the x alone, and the derivative of the other would be 1/2 4 minus x to the negative a half times a negative 1. So I did that chain rule. Plus, derivative of x is 1, so I can just leave that alone and write 4 minus x to the half. And now let's do some cleaning up. So this is negative 1/2 x times 4 minus x to the negative half plus 4 minus x to the half. And back when we were doing the product rule, that was a fine answer, but now I actually have to set this equal to 0, and that's going to be much easier if I go through and factor this and clean it up as much as possible. It'll be easier to set equal to 0 and to find where it's undefined. So let's do that. I'm going to factor out that, let's see, 4 minus x to the negative a half. And what am I left with? I'm left with a negative 1/2 x. And then I'm left with plus 4 minus x. When I factor out the 4 minus x to the negative a half here, remember 1/2 minus a negative a half is a 1, so I'm left with 4 minus x to the first power. All right, and keep going. I'm going to clean this up. I'm going to move that 4 minus x to the negative a half to the bottom. So that will be a 4 minus x to the positive a half down there. And then up top, I'm going to combine some like terms. I have a 4 as my constant and minus 3/2 x. So notice what this does is just puts it in a much nicer version, so I can set it equal to 0 and see where it's undefined. So f prime of x equals 0. Well, that is going to be where my numerator is 0. So 4 minus 3/2 x equals 0. And I'll solve for that. So 4 is 3/2 x. Multiply both sides by 2/3 to cancel out that fraction. And I get 8/3 equals x. So that is a critical point. And then f prime of x undefined. Well, it's going to be undefined if the denominator is 0. So square root of 4 minus x, when is that equal to 0? Well, that's going to be when x is 4, right? If we plugged in a 4, that would be a problem. So I've come up with two critical points there. So let's list them. So my endpoints, negative 2 and 4, and then I had that 8/3. Oh, and so 4 was a critical point, and it was an endpoint as well. So let's plug into f of x. What do we get? If we plug in a negative 2, we get negative 2 times the square root of 6, which will approximate that to negative 4.9, just to kind of get a feel for where that is. If we plug in an 8/3, we get 8/3 times the square root of 4/3. And if we want to approximate that to get a feel, we can. That's 3.1. And then if we plug in a 4, that'll be 4 times 0. So we're just getting a 0 there. So it looks like I have an absolute min at negative 2 and an absolute max at 3.1. 3.1, excuse me. So absolute min is at negative 2 comma negative 2 square root 6, and absolute max is at 8/3 comma 8/3 times the square root of 4/3. Maybe there's a better way to write that, but I'm not too concerned. There it is. All right, so that is how we find absolute extrema. We need to look at a continuous function on the closed interval. If we have that, we're guaranteed to have a max and a min. Then we can find the derivative, see where that derivative is equal to 0 or where it's undefined. That gets us our critical points. We list all of our endpoints and critical points and plug them into the original. The biggest y value is your absolute max, and your smallest y value is your absolute min.